Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
This video is going to introduce to you how to graph rational functions. When we say rational functions, we're literally referring to any one that has some kind of f of x over some kind of g of x. So we're talking about where you definitely have variables in the denominator. Not always do you have them in the numerator, but you have to have that denominator going on. So you will always have variables in both spots to be considered a rational function. So if I have 2 over x, this graphs as a rational function. If I have x over 2, it is not a rational function because it's actually linear. And the reason for that is I can rewrite it as 1/2 times x. So the variable is not in the denominator. These are the ones that we're looking at in this video, is rational. Now, rational can also have variables in both the numerator and the denominator. So when you're graphing rational functions, it is really important to find key features. So that's what we're going to focus on. So key features to look for. And if you can get these key features, you're going to have a pretty awesome basis for a graph. So the x-intercept. You can have more than one. Now, if you remember correctly, the x-intercept, if you look at a graph, it's going to be on an x-axis, meaning it's something, comma, 0. So to solve, you will substitute y equals 0 and solve. And if you've watched my other videos, you found several ways that we can solve when something equals 0. Your next key feature is going to be the y-intercept. Okay, you cannot have more than one y-intercept. If you do, it's not a function. So the y-intercept is 0, comma something. So here, we will substitute x equals 0 and solve. The next big thing you need to know are domain errors. Domain errors are anything that make your calculator say, I can't do this. There are generally two main domain errors, and it's when you have that's not working. A negative number when you have an even index, or when you have a number divided by 0. You cannot do that. So 0 in the denominator. And those are the kind of domain errors we're really going to be focusing on. So domain errors are caused in today's lesson by the denominator equaling 0. Now, the domain error can cause a vertical asymptote or a hole. I'll abbreviate vertical asymptote, hole. So a vertical asymptote would be like if I had 1 over x minus 5. And so the vertical asymptote is going to happen because of this domain error that is at 5. The hole is going to happen, for example, if you had like x plus 3 over x minus 4 or sorry, times x minus 4, and that's over x plus 3. And that's because the negative 3 is a domain error on the denominator and also happens to be in the numerator. Because these cancel out, it's no longer an asymptote, it becomes a whole. It's what's called a removable discontinuity. And wholes are something like, I think of it like this. If you were looking at an aerial of the county you live in, you're probably not going to see a teeny tiny bridge. However, if there's a river going through the county, that's going to be more of like an asymptote. You can't just like, you know, put in a culvert and you're fine. You've got to actually put in a big bridge. Okay, or compare it to like a culvert for a ditch and the Grand Canyon. So keep in mind, a hole is just a little bitty teeny tiny blip, whereas a vertical asymptote is very large. Once you find the domain errors, then technically you have found the vertical asymptotes and holes. Those must be notated on your graph, so it's always important to find all asymptotes. Vertical. Again, those are your domain errors. And horizontal or oblique. Okay. The way your horizontal and oblique asymptotes are found is by dividing, and you ignore the remainder. A horizontal asymptote is exactly what it sounds like. It's horizontal. But some graphs have what's called an oblique asymptote. I've seen linear oblique asymptotes. I've seen quadratic oblique asymptotes. I'm going to show you an example of what a linear oblique asymptote looks like. You might see a graph that has a line like this and a vertical asymptote like this. And the graph might actually be like this itself. And again, the whole point of an asymptote is to indicate the end behavior. So if you'll notice the horizontal, or sorry, the diagonal line here, the linear line, is approximating these areas, and the vertical is approximating these arrows. So asymptotes are just indicators of end behavior. Now there are some tricks so that you don't actually have to divide for horizontal and oblique. So if you have something like x plus 8, we're going to go x squared plus 8 over x cubed plus 12x plus 2. When you go to divide this is kind of like trying to divide 2 divided by 7. It's less than 1, right? 7 doesn't go into 2, it's all remainder. Well, the same thing here. X cubed doesn't go into x squared, it's all remainder. So when you divide x cubed plus 12x plus 2, it's going to go in 0 times. So you're going to have a horizontal asymptote at y equals 0. And this is because this power is smaller than this power. It's bottom heavy, kind of like this is bottom heavy. Okay. Forgot to write f of x or y. If you have something like f of x equals 8x cubed plus 5 over 4x cubed minus 2x plus 2. Okay, now instead of it being bottom heavy, the top power matches. So when I divide 8x cubed plus no x squared plus no x plus 5 divided by 4x cubed plus no x squared minus 2x plus 2. Oh my placeholders in there. 4 times 2 is going to be 8x cubed, and I will multiply. If you do not know how to divide these, you can go back and watch my video on division of polynomials. And we get 4x plus 1. And this power is smaller than this power, so that's all the remainders. So I said divide and ignore the remainder, right? Well, wouldn't I have been able to just do 8 divided by 4? Yes, I could have. So when the degrees match, just use your lead coefficients. You'll have a horizontal asymptote at y equals 2. Okay, so when it's bottom heavy, it's going to be horizontal asymptote at 0. When the degrees match, you can use the lead coefficients. If you're not in one of these two scenarios, then that's when the oblique asymptotes happen, and you have to divide and ignore the remainder. There's no way around it. So for these two type scenarios, when the degree of the bottom is bigger, or the degrees match, it's either going to be 0 or use the coefficients, and it's going to be a horizontal asymptote. If the degree of the top is bigger, that's when an oblique asymptote happens. A lot of times at the Algebra 2 level, you do not see the oblique asymptotes, you only see the horizontals. But depending on what classes you take after this, you might need that as well. Or if you are in college algebra, you might be looking at obliques. Okay, so we are going to graph y equals 6x over 2x plus 1. And we know that we need to start with our key features. So the easiest one to find, I believe, is the y-intercept. Again, that's 0 comma something. So y equals 6 times 0 divided by 2 times 0 plus 1. Okay, the y-intercept happens to be 0. Okay, so now let's do the x-intercept, or plural, right? Because we could have more than one. That would be something comma 0. So 0 equals 6x over 2x plus 1. When we multiply that 2x plus 1 over to the other side, we get 0 equals 6x. Will that always happen where when you multiply your denominator over, that you'll just be left with the top? Yes, absolutely. In fact, just a quick note, shortcut, the top gives you your x-intercepts, and the denominator gives you your domain errors. In other words, what x cannot be. Okay, so the numerator tells you where you cross the x-axis, and the denominator tells you, hey, where are your problem areas? So in this case, 6 times x equaling 0, we only get 0. So 0, 0 is the x and the y-intercept, and we don't have any other x-intercepts. Okay. Our domain errors. Two x plus 1 is on the bottom, and the bottom cannot equal 0. So 2x cannot equal -1, so x cannot equal -1/2. And since it does not cancel out, we have a vertical asymptote at x equals -1/2. Okay. Now the horizontal or oblique. And again, I'm going to do it the proper way. You can do that little shortcut way. So you might be testing out the shortcut and already knowing, but to get this, I'm going to divide and ignore the remainder. 2x goes into 6x 3 times. Oh, I forgot my placeholder. That leaves me with a remainder of -3 because there's no variable on here. The degree is less. Therefore, I have a horizontal at y equals 3. Okay, let's get all these key pieces on a graph really quick. I do want to go ahead before I graph this and add one key side note. Yes, this is 6x over 2x plus 1 is equal to 3 plus -3 over 2x plus 1. We can actually see an HK shift if I play with the writing a little bit more. Let me make this -3 over 2x plus 1 minus 3. I'm going to divide top and bottom by 2. Now we can see our HK shift of left 1/2, down 3. Or that was a positive 3. Why did I write a -3? Oops, sorry. Left 1/2, up 3. And if we see our asymptotes are at left 1/2 and up 3. So it is related. This is just how do I write it when it's not in that special HK shift format that I showed in the reciprocal function video. So the points of today's video is to be able to graph from a problem that just has a numerator and a denominator. Okay, so we said a vertical asymptote left 1/2. A horizontal up 3. And remember, these brown dashed lines are going to be kind of my guidelines for my graphing, kind of like you have coloring lines when you go to color something. We also said that we were going to cross the x and the y axis at 0, 0. Okay. From this, I've done enough of these graphs to know that this is probably like that reciprocal function, and it probably goes here and here. But because you probably do not know that, you have two options. You can make a table of values, or you can utilize a graphing feature such as Desmos to help you out. Let's get that bright light off there. Okay, so I like to do the division sign first. We had 6x in the numerator. And in the denominator, we had 2x plus 1. Okay. And here we go. Now we said that y equals 3 was our horizontal asymptote, and we can definitely see that it is flatlining around that y equals 3, no matter how far I zoom out, right? Bring it back in. And we had that vertical at x equals -1/2. And we can definitely see that, yes, that is also again making, and we can see our crossing at 0, 0. So all those key features did come out. Desmos supported that. So if you're in a class that allows utilizing a graphing utility, then by all means do that, and it'll help you get some extra ordered pairs. Or you can make your ordered pairs on your own, and I'm just going to do a rough sketch to finish this out. So our domain is -infinity to -1/2, or -1/2 to infinity. And our range happened to be -infinity to 3, or 3 to infinity. And just in case you need it, the limit as x goes to infinity, meaning as x goes to infinity for our equation. This is just another way of writing end behavior. So as x goes to infinity, y is getting closer and closer to 3, and it's slightly below. That's another way of writing as x approaches infinity, y approaches 3. So depending on how your textbook is working things out, then you have that. Okay, let's look at another one. Let's get a little more complicated here. Okay, just in case you need it, I'm going to remind you that 3x squared minus 12 is the same as 3 times x squared minus 4, which is the same as 3 times x plus 2, x minus 2. And the numerator, what multiplies to 4 and adds to 5, that would be x plus 4 and x plus 1. So they have it written as a multiplied form. I have over here to the side the factored form. Okay, so y-intercept, first step, right? So the y-intercept, if I substitute 0, what do I get out? Okay, 0 squared plus 5 times 0 plus 4 over 3 times 0 squared minus 12. That would give us 4 over negative 12, so that would be negative 1/3. Okay, x-intercept. That means we're popping 0 in for y. Now remember, we could have more than one of these, right? So 0 equals x squared plus 5x plus 4 over 3x squared minus 12. When I multiply this to the other side, it gives me 0 equals x squared plus 5x plus 4. Or 0 equals x plus 1, x plus 4. Hey, that factored form from right there? Yeah. So we're getting 2 zeros, it looks like. Negative 4 and negative 1. Now we have to be careful that they're not domain errors. So let's double check our domain errors. Because of the denominator, x cannot equal 2 or negative 2. Those are bad numbers. And we did not use either of those x values, so they both work. And nothing cancels, so x equals 2 and x equals negative 2 are vertical asymptotes. Go ahead and get this information that we have so far on here. Yes, it's okay to have multiple vertical asymptotes. Will they always be at the same numbers, like 2 and negative 2? No. Okay. We had a y-intercept of negative 1/3, an x-intercept of negative 4, and an x-intercept of negative 1. Okay, that's a little bit interesting. So now we want to go ahead and we want to get that oblique asymptote or horizontal asymptote, depending. Now, since this time I'm just going to do the trick. Because those are both x squared, our coefficients are going to be that horizontal asymptote. So that would be 1/3. So I'm going to come in here. Now some textbooks will say, do you cross the horizontal asymptote? So let's check. Here's our equation. Will it ever cross our horizontal asymptote? Meaning, substitute that y value. Okay, we have a proportion. Not a big deal, we can cross product. Okay. Right now it looks like quadratic, so we would set it equal to 0, but if I were to subtract 3x squared from both sides, it cancels out. So 15x plus 12 equals negative 12. So 15x equals negative 24. So x equals negative 24 over 15. They both divide by 3, negative 8 over 5, right? Or negative 1.6 if you're a decimal person. So yes, we cross the horizontal asymptote at x is negative 1.6. That'd be like right there. That's kind of an interesting shape going on. So it is possible to cross a horizontal asymptote. So I've done enough of these that I happen to know that the shape is going to be slightly below the horizontal asymptote, horizontal axis, and then come down here. And then there's a reason why this arrow goes down and then this arrow goes up. And it's because there are no exponents on our parentheses. That's why the arrows do opposites. And it's going to come down here and it's going to go through these points. And it'll continue its downward track. And then because this side is down, this side will be up. Okay. However, you may not have gotten to that point. So let's just check it out from the beginning. Come in here, division, x squared plus 5x plus 4. Wow. Okay, there we go. Get that off there. And we said x equals 2, definitely a vertical asymptote. X equals negative 2, definitely the other vertical asymptote. If you had put in the wrong number, like let's say you'd had 3, see how it just cuts through? It doesn't look like it's not cutting between the two shapes, it's crossing in a random spot. So let's pop that back. Okay, and then we said y equals negative 1/3. No, that was our y-intercept. Y equals positive 1/3 was our horizontal asymptote. There we go. And again, if you had said like negative 1/3, definitely not where the two sides are flatlining. And then if we come in here, we can see that it is crossing at negative 1.6.3 repeating. So, and if you ever need to, you should be able to hold down on these and change them to dotted lines if you want. So you can change your colors and things like that on Desmos. Okay. So thinking about it from a fraction standpoint, okay, when the top equals 0, you have x-intercepts. When the bottom equals 0, you have domain errors. Okay. If degrees match, then those lead coefficients is your horizontal asymptote. Okay? If this degree is bigger, you have y equals 0 for horizontal asymptote. If this degree is bigger, you got to do the work. And remember, you'll ignore that remainder. So that's a quick catch there. Now, I do want to go ahead and show you with Desmos as well what happens with this particular graph. Okay, so we can see right here, we have domain errors. So x cannot equal negative 3 and x cannot equal 5. So we want to say they're vertical asymptotes. But at the same time, we want to say x equals 3 and x equals 2 is where it's going to cross the x-axis. Sorry, negative 3. But see how negative 3 occurs in the top list and the bottom list? So what does that do? Okay. So again, when I'm using this, I like to do my division sign first. So we had x plus 3 x minus 2 and a denominator of x plus 3 and x minus 5. Okay. So we kind of expected there to be an issue at x equaling negative 3, but there's not. And we expected there to be one at x equals 5, and that definitely does exist. And the reason why the horizontal is at y equals 1 is because if you were to multiply the numerator together and the denominator together, they would both start off with 1x squared, and 1 over 1 is 1. So what's going on here at negative 3? It looks like the graph exists. It looks perfect. But let's see if I can... I think my finger will be in the way if I try to do it. Yeah, that's not counting as a stylus. So there we go. Closer. Oh, if I can get it, there it is. So see how it's saying undefined? And if you do this with a mouse, I forgot I have my mouse. No, my mouse is not attached to my iPad. If you do this with a mouse on your computer, it'll actually show a hole at negative 3. And if you have it add in a table of values, you can type in negative 3 and it will be undefined. So you have to really, it's kind of fun, but really, really, really zoom in. Ooh, please tell me, yep, negative 3 is still there. We are zoomed way in. I forgot how far you have to go to get it to. It will not let me zoom anymore. We are you can almost see the hole. There it is. You can see how it's kind of an open circle underneath my finger. There, I finally got it shown. If I move off, I'll finally, I'm zoomed in so far, it still thinks everything is negative 3. So it's still thinking everything is negative 3. I am zoomed in really far. It's not even giving me decimals on the bottom. Let's just zoom back to home. Okay, now we have dots on there. Obviously negative 3 is not going to be placed on there because it's a very, very teeny tiny gap. So if you were to do this problem, you would say that a vertical asymptote exists at x equals 5 and a hole exists at x equals negative 3, and that's because it's removable or fixable. Like if I were to put the reduced equation in, it would no longer be an issue. However, our domain is always done from an unreduced standpoint. Now I do want to go over the domain and the range for this particular equation that we did a moment ago. So our domain, we have to skip these numbers. So x is from negative infinity to negative 2, or negative 2 to positive 2, or 2 to infinity. And we normally would skip that horizontal asymptote of 1/3, but Right here we crossed it, so our range is actually all reals for the y. We didn't actually skip any. So please be careful of making sure you double check where's your domain, where's your range, where is your vertical asymptotes, where's your holes. Those are the key features that guide everything about the graph. You can build a table of values around them, but if you know those key features, you'll be well on your way to graphing.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Then drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.